2,000 years ago, Roman builders constructed walls nearly a meter thick, faced them toward the sun, and achieved something most modern homes still cannot: stable, indoor warmth with no fuel at all. These walls absorbed the day's heat and released it 12 hours later like a slow-burning furnace, cutting heating costs to essentially nothing. Then, in barely a generation, the method was abandoned entirely. The reason has less to do with performance than you would think. Across the Roman Empire, city planners and builders relied on a set of design rules that went far beyond ornament or style. In the heart of Rome, entire apartment blocks, known as insulae, rose on foundations of stone and concrete, their walls often reaching 0.6 to 0.9 meters thick. These were not accidental dimensions. Roman builders, guided by the treatises of Vitruvius, oriented their main facades to the south, capturing the low winter sun and maximizing solar gain. The thickness of the wall was chosen to create a deliberate time lag between the outside chill and the warmth inside, allowing the day's heat to be stored in the dense core and released slowly through the night. Archaeological surveys of surviving insulae confirm this pattern: thick masonry cores, brick facings, and a consistent alignment with the sun's path. These walls were not just barriers, they were engineered to moderate the Mediterranean climate, flattening the swing between cold nights and hot afternoons. The approach was so effective that similar strategies appeared from North Africa to the Levant, each adapted to local materials, but sharing the same underlying logic. In every case, the builder's choices reveal an understanding of solar orientation and thermal mass that predates modern building science by nearly 2 millennia. The Roman precedent stands as proof that massive, sun-facing walls were a global solution, not a local curiosity, and that their adoption was rooted in careful observation and practical experience. Adobe begins as a blend of what's underfoot: clay-rich soil, coarse sand, and just enough straw to bind it all together. The classic recipe, about 3 parts earth to 1 part sand, with a handful of chopped straw per batch, creates a mixture that can be pressed by hand or formed in simple wooden molds. Unlike fired brick or concrete, adobe needs no kiln, no fuel, and almost no imported materials. Each brick is shaped wet, then left to cure in the open air for up to 6 weeks, hardening under the sun's heat and the region's dry winds. This sun-drying process locks in strength while using almost no external energy. The result is a solid block that weighs nearly 30 pounds and holds its shape for generations. Builders stack these bricks in thick courses, using more of the same mud as mortar. Straw fibers help resist cracking as the wall dries and ages, while the sand keeps the mixture from shrinking too much. The wall's density, typically from 1,600 to 1,800 kilograms per cubic meter, gives it extraordinary thermal mass. Every layer, from the rough core to the finished surface, is shaped by hand, with each step tuned to the local climate and available resources. This low-energy craft stands in sharp contrast to the high-heat, high-carbon processes of modern materials. Adobe's embodied energy is among the lowest of any building method. No kiln firing, no cement, no steel. Each brick is a direct translation of earth and sun into shelter, setting the stage for the physical principles that make these walls so effective at storing and releasing heat. A wall made from adobe or stone is more than a barrier. It is a kind of thermal battery. During the day, sunlight strikes the exterior, and heat begins to move inward by conduction. The dense material absorbs this energy, storing it deep within its mass. But the process is not instant. Thanks to the wall's thickness and high heat capacity, the warmth travels slowly, creating a measurable delay between the peak temperature outside and the rise inside. Building scientists call this the phase lag. For a typical 0.3 meter adobe wall, the delay is about 12 hours. That means the heat absorbed at noon does not reach the interior surface until midnight, just when it is needed most. The effect is more than theoretical. Field studies in Taos Pueblo have recorded winter nights where the indoor temperature remains stable, even as outdoor readings plunge below zero. Sensors placed at different depths confirm a steady, gradual migration of warmth through the wall, flattening the temperature swings that would otherwise make the house unlivable without fuel. The math behind it is straightforward. The wall's density, specific heat, and thickness all combine to slow the flow of energy, stretching a single sunny afternoon's warmth across the long, cold hours of night. Dr. Lisa Heschong, a leading building science expert, summarizes it this way. A well-built thermal wall does not just store heat, it times its release to match human comfort. This principle allowed ancient builders to achieve lasting comfort with no mechanical intervention, relying only on the physics of heat and the careful choice of material and orientation. In the years following World War II, the American housing market underwent a dramatic transformation. Between 1950 and 1975, annual sales of HVAC units in the United States soared from around 1 million to over 10 million. This surge wasn't just a matter of consumer preference, it was built into the very framework of new construction. Building codes, rewritten to emphasize insulation values, and standardized assembly began to favor lightweight walls filled with fiberglass or foam. The International Building Code, introduced in the 1960s, set minimum R-value requirements that effectively limited wall thickness and sidelined the use of dense heat-storing materials. Architects and builders, now guided by regulations and a booming market for mechanical comfort, shifted toward designs that prioritized rapid assembly and compatibility with central heating and cooling systems. The economics were clear. Lightweight construction reduced labor costs, sped up building schedules, and allowed for easy integration of ducts and wiring. As a result, the knowledge and craft behind thermal mass walls faded from mainstream practice. The promise of instant temperature control, reinforced by advertising and code mandates, replaced the slow, steady warmth of passive design with a push-button solution, one that depended on a constant flow of energy rather than the rhythms of the sun and the seasons. In the old city of Sana'a, the survival of Yemen's towering mud brick houses depended on a rhythm of care as much as on engineering. Every 5 years, families and neighbors gathered for a ritual that began at sunrise, the renewal of the outer plaster. The process unfolded in 3 distinct stages. First, the walls were cleaned and moistened, activating the lime in the base layer. Next, a rough coat of mud mixed with straw and animal hair was pressed by hand to fill every crack and hollow. Finally, a fine, earth-colored plaster was burnished onto the surface, sealing the building against rain and desert wind. This was not just maintenance, it was a social event, a moment of community. Labor, water, and food were shared, and the work itself reinforced bonds between households. For Master Mason Abdulaziz Al-Hadri, who has spent decades preserving Sana'a's historic towers, the ritual is as much about passing on knowledge as it is about protecting the building. Without this cycle, cracks would open, moisture would seep in, and the wall's ability to store and release heat would fade. The performance of the thermal wall, in other words, relied on human hands as much as on material science. When the communal upkeep stopped, so did the wall's resilience, a trade-off that modern builders rarely consider when choosing fast, energy-intensive systems over time-tested craft. In Taos, a new generation of builders set out to prove that ancient thermal wisdom could meet modern standards for comfort and efficiency. The Green Pueblos project began by preserving the original adobe walls, thick, sun-dried bricks that had already stood for a century, and pairing them with a thin layer of phase-change material panels on the inside. These phase-change material panels, only a few centimeters thick, store and release heat as they change from solid to liquid and back again, amplifying the wall's natural ability to buffer temperature swings. Over the course of a full winter, sensors tracked the performance of these retrofitted homes. Even on nights when outdoor temperatures dropped below freezing, the interiors held steady. Warmth gathered during the day was released slowly, keeping rooms comfortable without activating a furnace. Annual heating energy use dropped to near zero, with utility data showing a 94% reduction compared to pre-retrofit levels. The original adobe, untouched on the exterior, continued to provide mass and durability, while the phase change layer fine-tuned the timing of heat release. This blend of old and new demonstrates that passive design is not just a relic, but a practical, scalable path forward. By combining traditional thermal mass with modern materials, builders achieved net zero heating in a climate where winter once demanded constant fuel. The experiment stands as proof that the lessons of ancient walls still hold power, and that the future of low-carbon housing may depend on remembering what was nearly forgotten. Today, buildings consume nearly 40% of global energy, much of it just to fight the weather outside. As fuel costs and climate concerns rise, the science of thermal mass offers more than nostalgia. Sometimes, the most resilient solutions are the ones we left behind. What would you build now?